Hello viewers, welcome to video number 117 of the channel MALACHEMPHILIC, and this video is the 57th episode of Chemical Thermodynamics, where the topic is Fundamental Equations of Thermodynamics and Maxwell's Relations. So here is Dr. Mala Das Sharma, and let's start the topic. See, fundamental equations of thermodynamics. See, for any closed system means where no matter is transferred between the system and the surrounding, and another condition, only mechanical work is involved, that is pressure volume work is involved. In that case, from this first law of thermodynamics, we know that heat absorbed at constant pressure, we are considering heat absorbed, that is equal to this D, change in the internal energy, and this pressure volume work. And from the second law, we know that change in entropy is nothing but the heat exchange divided by the temperature at which this heat absorption or release occurs. So from here, TdS is equal to del Q, right? Then in place of this del Q, we write TdS. So TdS is equal to dE plus PdV. So therefore dE is equal to TdS minus PdV. So this is the first fundamental thermodynamic equation. dE is equal to TdS minus PdV. Now we see the second one. It is a fundamental equation of thermodynamics. Second one here with enthalpy, H is equal to E plus PV, we know. So if we take the complete derivative, so dH will be equal to dE plus this derivative, this differentiation. This differentiation is first function differentiation of the second, then second function differentiation of the first. So PdV plus VdP. Again, just now we have derived dE is equal to TdS minus PdV. So in place of dE, if we put TdS minus PdV, then what we are getting? If we put TdS minus PdV, then we are getting that dH is equal to, what we are getting? We are getting that dH is equal to our TdS minus PdV, then plus PdV, this plus PdV, plus VdP. So this PdV and PdV get cancelled, minus plus. So what is left over? dH is equal to TdS plus VdP. So our second fundamental thermodynamic equation is dH is equal to TdS plus VdP. Now coming to the third one. Third one is with Helmholtz free energy function or work function. We know A is equal to work function is equal to E minus Ts. Now once again we will take the derivative, complete derivative of this equation. So dA will be equal to dE minus this complete differentiation, first function differentiation of the second, and then second function differentiation of the first. So TdS minus SdT. Now once again dE is equal to TdS minus PdV. We are putting in place of dE. So dA will be equal to now TdS minus PdV, right? Minus TdS minus SdT. Now here you see TdS and TdS are getting cancelled. So dA is equal to minus PdV minus SdT. So this is our third fundamental thermodynamic equation. dA is equal to minus PdV minus SdT. Now coming to the fourth one. Fourth one gives free energy function. We know G is equal to H minus Ts. Now Again, H is equal to E plus PV. So, G is equal to E plus PV minus Ts. Now, we take the complete derivative. So, dG will be equal to dE plus PdV plus VdP minus TdS minus SdT. Same rule. First function differentiation of the second plus second function differentiation of the first. Again, dE is equal to TdS minus PdV. We'll put it in place of dE. So, what is there now? dG is equal to TdS minus PdV in place of dE. Then PdV, that is plus PdV plus VdP minus TdS minus SdT. Now, look at here. Here, TdS and this TdS are getting cancelled, and also PdV and PdV are getting cancelled. So, what is left over? dG is equal to VdP minus SdT. So, our fourth equation is dG is equal to VdP minus SdT. So, therefore, if we combine all these four equations, so first one, dE is equal to TdS minus PdV. Second one, dH is equal to TdS plus VdP. Third one, dA is equal to minus PdV minus SdT. And fourth one, dG is equal to VdP minus SdT. So, these four equations are regarded as fundamental thermodynamics equation for closed system. That means where the compositions remains constant. Now, using these four fundamental equations, we will derive this Maxwell relation. So, from these four fundamental thermodynamic equations, another four relations which are extensively used in thermodynamic calculations can be derived. And these are known as Maxwell's relation. So, let's start. Now, look at here. So, first one here, what we have observed that this first equation we have taken here, that is dE is equal to TdS minus PdV. Okay. So, what you have to do, I already have written here. Here, first you have to differentiate. Differentiating this equation with respect to S, that is entropy, at constant volume, followed by reverse one. Differentiating with respect to volume at constant temperature. So, what is the first one? We have to differentiate with respect to S. So, dole E by dole S, and here which one is constant? Volume is constant. So, if we differentiate with respect to this entropy, look at this equation. In this equation, ds by ds will be 1. That means it will be T, right? And at constant volume. So, dV part will be is equal to 0. Now, what you have to do? Once again, you have to differentiate now reverse way with respect to volume. So, it will be dole square E by dole V dole S. Okay. With respect to volume at constant entropy. So, this one will be is equal to dole T with respect to volume, that is dole V at constant entropy. Now, coming here. Same thing we will do, but in the reverse way. Here first we will differentiate with respect to volume at constant entropy. So, what it will be? Dole E by dole V at constant entropy. So, what it will be? dV by dV is equal to 1. So, it will be minus P, and constant entropy means ds will be 0. Now, once again, we have to differentiate with respect to entropy at constant volume. So, it will be dole square E by dole S dole V is equal to minus dole P by dole S at constant volume. Right? Now, since, we'll write here, since D is exact differential differential. So, therefore, what we can write? This dou square E by dou V dou S is equal to dou square E by dou S dou V. So, that means this is equal to this. So, what we can write? Therefore, this dou T by dou V at constant entropy is equal to minus dou P by dou S at constant volume. So, this is this first Maxwell relation. So, second one is dH is equal to TdS plus VdP. So, here what we have to do? First, you have to differentiate with respect to S entropy at constant pressure. So, dou H by dou S at constant pressure, that will be is equal to dou S, ds by ds1, so it will be is equal to T, and constant pressure means dP is equal to 0. Next, what you have to do? We have to differentiate with respect to pressure at constant entropy. So, dou square H by dou P dou S, that will be is equal to dou T by dou P at constant entropy. Okay. Now, this side what it will be? Just in the reverse way. First, you have to differentiate with respect to pressure. So, dou H by dou P at constant entropy S. Then, dP by dP is equal to 1. That means it will be is equal to V, and as entropy constant, ds is equal to 0. Next time, just in the reverse way. So, dou square H by, now with respect to entropy at constant pressure, dou S dou P is equal to, that is dou V by dou S at constant pressure. Okay. Now, once again, dH is an exact differential. Therefore, this dou square H by dou P dou S is equal to dou square H by dou S dou P. This is equal. So, that means this is equal to this. That means this dou T by dou P at constant entropy is equal to dou V by dou S at constant pressure. So, this is the second Maxwell relation. Okay. Now, you see the third one. Third one from the third equation, that is dA, work function, dA is equal to minus PdV minus SdT. So, here what we have to do? We have to differentiate with respect to volume at constant temperature. So, dou A by dou V at constant temperature, that will be is equal to temperature constant. So, dt part will be 0. So, minus P, dV by dV is equal to 1. Now, once again, with respect to temperature at constant volume. So, dou square A by dou T dou V is equal to minus dou P with respect to temperature dou T at constant volume. Now, here in the reverse we will do. That means with respect to temperature at constant volume. So, dou A by dou T at constant volume. How much it will be? dt by dt is 1, so it is minus s, and constant volume means dv is equal to 0. So once again you have to differentiate reverse way. So now it is with respect to volume at constant temperature. So dou square A by dou V dou T is equal to minus dou S by dou V at constant temperature. Now once again here also, as dA is an exact differential, so once again this is this dou square A dou T dou V is equal to dou square A this dou V dou T. So this is equal to this, that means this is equal to this. So what we can write? That is dou P. Therefore, dou P by dou T at constant volume is equal to, both the side minus is there. Okay, I write here minus first. Minus is equal to minus dou S by dou V at constant temperature. Both the side minus is there, no? So what we can write? Change of pressure with respect to temperature at constant volume is equal to change of entropy with respect to volume at constant temperature. So this is our third Maxwell's relation. This is the third one. Now we see the fourth equation. Fourth equation is with Gibbs free energy. dG is equal to VdP minus SdP. So first differentiating with respect to pressure at constant temperature. So dou G by dou P at constant temperature, that is equal to, now dP with pressure. So dP by dP 1, so it is only volume V, right? And dt, constant temperature means dt is equal to 0. Now once again in the reverse way, that is with respect to differentiation with respect to temperature at constant pressure. So dou square G by dou T dou P is equal to dou V by dou T at constant pressure. Now here this side, we'll start in the reverse way. First with respect to temperature at constant pressure. So dou G by dou T at constant pressure is equal to, pressure constant means dP will be 0. So here it will be only minus S. Next with respect to pressure at constant temperature. So dou square G by dou P, then this dou T is equal to dou S minus dou S by dou P at constant temperature. Now once again the same thing, as dH is an exact differential. So this dou square G by dou T by dou P is equal to dou square G divided by dou P dou T. These are same. Therefore, what we can write? Therefore, we can write here that dou V by dou T at constant pressure is equal to minus dou S by dou P at constant temperature. That means change of volume with respect to temperature at constant pressure is equal to minus of change of entropy with respect to pressure at constant temperature. These two are same. Why? Because as I told you, it is an exact differential. I didn't write here. Let me write. Dou square G dou T dou P is equal to dou square G dou P dou T. Okay. So since this is same, so therefore this is. So this is our fourth Maxwell relation, right? This is the fourth Maxwell relation. So therefore the Maxwell's relations are this one. This first one is, what is the first one? That is, change of temperature with respect to volume at constant entropy is equal to minus of change of pressure with respect to entropy at constant volume. Second one, change of temperature with respect to pressure at constant entropy is equal to change of volume with respect to entropy at constant pressure. Next one, change of entropy with respect to volume at constant temperature is equal to change of pressure with respect to temperature at constant volume. And last one, change of volume with respect to temperature at constant pressure is equal to minus of change of entropy with respect to pressure at constant temperature. These four Maxwell's relations are used extensively in thermodynamic calculation. So, hope you have understood. Thank you.